Thank you for the kind introduction. This is great. Thank you for being here on a Saturday. I know this is quite a long run after 4 days of conference, and also thank you for waiting for a little bit of the technical hiccup here that we had. Yeah, that's exciting. It's an exciting time to be around as a data scientist. It's an exciting time to see the development of new technology and of new capabilities emerging basically faster than we can catch up normally, right? So today we're taking some time to talk about data visualization. And I think I want to actually, before I get started here, I want to take a step back and say, I think we've had some great talks on data visualization and on storytelling with data. For example, I think of Isaac Reyes yesterday was a very well-received talk and a great way to show how you can tell stories around data. Today, for me, it's going to be a little bit on storytelling as well, but actually also on more of the theory behind data visualization and how it fits into the data science stack in a way. And then, so please be prepared for around probably, I want to say 30, maybe a little bit more than that, 30, 45 minutes of a kind of a discussion of technical elements and theoretical elements and kind of underlying framework of data visualization. Please do interrupt me with questions along the way. I think we have plenty of time, and then I think towards the second half of the session we'll have some time to go through an R-Shiny app and to go through some advanced graphs in R as well. All right, so first of all, I want to actually start with some credits aside from the sessions that I just pointed out. This is actually just giving some credit, for example, that on talking about some of the foundation of this session is based on is mostly a book from Tamara Munzner. She's a professor at British Columbia in Vancouver. It's a great book. I encourage you to check that out, which has a lot of great references on stylistic elements that are being used in data visualization. Also some inspiration that I got from my time at UC Santa Barbara, where I was in the visualization lab and I took some classes there. And there's also some inspiration I got from DataVis at Caltech. So to the talk, we'll spend quite some time to talk about why do we actually care about data visualization and what are some of the challenges that data scientists and other practitioners are facing. Then we'll talk about some of the technical tools and elements we have handy available. Then some graphs in R and actually some advanced graphs that can be used to do the storytelling with data or also use data visualization really as a key technique to be successful as a data scientist. Then we'll talk about some more emerging data visualizations on a fairly high level, and then we'll have the R exercises as well. All right, so I want to kick this off with the, I call it data science skillgram. So I think many of you have seen this. I'm showing nothing new here, but it's really the triage of math skills, stat skills, then computer science and knowing how to code somehow, having some programming skills, and then the domain expertise, right? That's really what the current background, a very interdisciplinary background for a data scientist is. So I'd like to pose a question here. Where do you think actually data visualization falls on that graph? Any guesses? So I'm hearing. Who thinks it's math and stats mostly? No one? Okay. Who thinks it's computer science? Some of it? Okay, and who thinks it's for the domain and business knowledge? Okay, mostly that, right? But I would say it's actually, who thinks it's at data science? It's actually jointly needed in all those fields. Yeah, so it's really key actually in being successful. It's kind of like you're doing all the hard work, right? I think there's this famous joke that as data scientists, we really spend 90% of our time doing all the data monging and kind of the data prep and getting our data sources all set up, and then we're doing 10% explaining why the models don't work, right? So I would actually go further and say you go another 10% on, or you maybe take even that 1% in practice to work on database. And I think that 1% is not enough. It should really be maybe another 10% and hopefully showing why your models did work in a way too, or why you can get some insight out of the maybe dysfunctional models, right? So going from the skillgram to the data science stack, don't get too overwhelmed here. There's a lot going on. We could spend the whole 2 hours talking about it. We won't. But it's a graph and it's data visualization. But what I want you to see is just take the 30,000-foot view where it's, okay, you really have data viz all along the way of that data science stack, right? It starts with, even it's something simple as looking at your raw data, maybe in a text editor, right? Text editor of choice, or maybe in Microsoft Excel if you're adventurous. Then go into descriptive stats layer, right, where you have your bar charts, your descriptive stats. Go into the diagnostic layer where you look at relationships, causes between the data. Go into the predictive side of things where you actually try to forecast, you try to understand what it takes to look ahead in time, and then go and actually to the semantic layer where you have kind of really advanced data visualizations, right? So I really argue as data scientists we really need to be data viz savvy along that whole process, right? And we need to iterate and make use of visual interpretations of the data. Oftentimes it's actually a great tool when we're stuck to actually not be stuck, right? And to actually kind of take a step back and try to put your data in a graph. And then I would even go further and say, not just create that graph with your code, but actually also maybe take the graph and go to your coworker or go to your neighbor and try to describe it, try to describe what's going on. Because often you realize that's where you're actually stuck. And that's where if you can't have a good description for your graph, maybe there's something else wrong. And you need to first build a graph that you can actually describe and have a result from. So more formally, I think data visualization is a means to augment human capabilities to view and interpret data. So that's really the key here. It doesn't really work without the human element in it, right? But it also helps us at the same time to get a better view on our data, which otherwise would be way too, let's say, high dimensional, way too complex to actually explore just in that text editor or in Excel, right? So it really helps us as a tool to augment underlying data sets that we then perform, all those steps along the data science stack that I just talked about. And then finally, obviously, having your models and having your results that you bring to your audience, right? So I think that point was very well taken yesterday. In Isaac's talk, we talk about the 4 elements. Well, the first one is actually know your audience, right? So really what you're doing here is you're augmenting your data, you're creating a graph, and then you're taking it back to your audience to deliver a result. More technically, you have things like understanding relationships between factors. Great. Okay, that's a scatter plot, technical things that you can use that for. You can actually by now do like much more higher dimensional plots. I mean, 3D, 4D. People are trying to pack in 5D into graphs. We'll see some examples there later. There's recognizing patterns, of course. That's when the stats fail, I would say, or when the scatter plot doesn't even show you anything. Then you're trying maybe to use a much more advanced visualization technique. Maybe you look into D3, you look into processing, some of those examples, and just map out the data in every way, shape, or form you can, or create another cut of the data, slice and dice it, create another aggregate, maybe take samples from it, and see if you can find any type of patterns. Breaking down complexity or dimensionality reduction, that's actually one of my favorites. It's often kind of it works without, you can do nonlinear dimensionality reduction through PCA or through other means without data visualization, right? But data visualization really goes extra mile here again to visualize, let's say, the results you get from PCA, and you're showing your 2 main axes of your variability. Finally, exploratory analysis, of course, related to recognizing patterns, I would say, but really as a means to basically just consume data and say, okay, we're exploring, and then we're actually maybe not even doing data analysis, but we're exploring some quantitative information, and out of a sudden we find something interesting, and we then start doing data analysis with it and start doing data science. So, but last but not least, really, again, key here is communicating results to collaborators, clients, friends. It often doesn't work, and it's just a great abstraction of something even more abstract, right? Where it's really easier to show an artificial neural networks in terms of an input layer, hidden layer, and output layer, instead of just writing down exponential equations, right? So it's a lot nicer. And then people, of course, go further and show images of the brain as well and say, okay, but it's still artificial. So it really helps to communicate clearly what's going on in math, but also what's going on in the computers, of course, and then relating that back to your domain. Does that make sense so far? Any pressing questions? Okay. So next we'll show where can data viz actually, how did data viz kind of, a quick history discourse here. Anscombe's quartet, I've seen it a couple of times in this conference actually so far, but I still like it so much I couldn't delete it. So what's going on here? Those are 4 graphs. Anyone want to take a guess, or anyone has paid good attention yesterday in Lindsay's talk? What's the story here? What is the value add of data visualization to that one? Is it okay? It's a good guess, but are they the same data? The 4 charts? Yeah, please. Yeah, so the stats are the same, right? So it's an example where data visualization, those stats are the same. Let's give it away, right? The mean is the same, variance is the same, mean of both x and y is the same. Your correlation between the two is the same. You fit a regression, you get the same result. Therefore, also your coefficient of determination, aka r squared, is also going to be the same. Well, point being is, if you don't go the extra mile to plot the chart, you might, if you only look at the right-hand side here, you might not see that actually you have 4 very different samples, and you have actually probably 4 very inherently different processes that generate those samples, right? So first one, x1, would just be simple linear plot with a little bit of a linear relationship, linear process going on, most likely a little bit of noise. The second one looks like kind of perfectly quadratic or maybe logarithmic kind of curve there that has no noise whatsoever, but it's not linear. Then you have a perfectly linear one in x3, but albeit having one outlier in there as well, that kind of then basically drags your regression line and your other sample stats back up to the same as we saw in x1. And then finally you have this blurb of samples that look more like a soil sample or something, or like a count data set there that is completely different than the rest, right? That might be your odd data set that you actually wanted to exclude from your analysis in the first place because maybe your sensor was messed up, or you did some human error in collecting the data, right? So that's great. So unfortunately it's not always that easy, right? And we're not quite having as much of an easy time as Anscombe had. Maybe he didn't have an easy time either, but I want to say this is a fairly simple example, shows the value of data viz. But if you look at what are some of the challenges in data visualization, it's actually, there's quite a bit going on. And there's your domain situation. This is kind of a nested model. It's from Tamara Menzer, the book that I mentioned in the beginning of this. It really talks about this nested model, or this nested problem set that you're facing when you're trying to be successful with data viz, right? So you're starting with, what am I trying to do, right? So that's probably, you're asking that question, of course, before you're generating your plot. You ideally ask that question long before you get started on your project, on any type of other, data prep and data modeling tasks that come before the visualization. But that's the first thing, right? And then after that, you say, well, if I have a question that I'm trying to solve, or a problem I'm trying to solve, here's the data I'm going to use, and here's the data I'm going to use on an abstract level to answer that question, right? That's the second one. And then the third one is the visual encoding. That's like saying, okay, now I have these data, how do I actually encode them and show them in an interaction, right? And you're showing problems here along that way. For example, the way you're showing your graph might just not work, right? You might be showing the wrong data, and then underlying that, you also you can have algorithmic problems where that one is actually more from computer science background, where it's saying, okay, your code is too slow. That's maybe only applicable to something if you're trying to produce real-time maps, say, of Twitter tweets, right? And you really need a very sophisticated back-end engine that can do well in pulling the APIs, pulling those tweets from the API in real time, and then doing the analysis and then generating the graph. So that's maybe not so applicable to most people's everyday work unless you do real-time analytics or you do heavy computing, very, very giant data sets, right? But it's becoming more of a problem as we're in the age of big data, and we have more and more basically big data sets, right, that require heavy compute. So then there was a framework that was being developed around that, where it's saying, well, and again, there's a lot going on in this one. This is actually the same box, but now instead of emerging problems showing some of the solutions, you don't have to read over all of that. That's fine. But you can see here on the left that it's really a highly interdisciplinary task to be successful, right? So you're doing things like using skills from anthropology or ethnography. What is that? What the heck does that mean, right? Any guesses? How does ethnography help you to understand your domain better? Any ethnographists in the room? Okay, that's what I was afraid of. That's okay. So it's fairly simple. It's just a fancy way of saying let's do surveys and ask what we need to do, right? Or what are, in business at least, or in industry, what do our customers actually want? What's the task at hand we're trying to solve? Ethnography can actually help with that. You can work with ethnographers or work with folks that have done a lot of surveys and are very good at asking the right questions to figure out needs, right? Then again, of course, design, we know that. We've seen some great examples of that this week. Visual design is very helpful to do cutting-edge data visualization and computer science at its root. So you really need to, and psychology, of course, where you're thinking about cognition on the one hand, you're thinking about perception, of human perception of the shown dimensions, right? So okay, that's great in theory. Putting this into practice a little bit, I was still unsatisfied when I read that. I think it's a great formalization of what's going on in data visualization and showing some of the challenges it takes to make a good graph, but it's not quite there yet. So from a practical standpoint, I'd like to add on this a little bit, where we're saying, okay, I think we're really faced with some other problems too, or some problems that are more technique related too, from how do we actually succeed at data visualization. So first, I think we have really too many choices often in graph types and platforms, right? So we're talking about graph types. There's a sheer endless type of different graphs, as we will see later, and as I'm sure you've seen in all your favorite tools of choice. But then there's also, the question is, should we do Excel? Should we do tools in R, tools in Python, D3? There's a lot of other new tools emerging. There's dashboards you can use to deliver your graphs. Today is going to be more a little bit about, making single graphs that we can use to communicate better and to communicate our results more effectively. But dashboard design is a whole other world, right? So that's one thing. So how do you pick how do you get through all these choices, right? And then how do you get the template or the choice that is most suitable for your data, right? That's actually a computational problem or an automation problem that has not been solved. It's called dynamic data visualization, actually. It has not been solved that for any given data set, I can find the best graph in terms of even the category of the graph, right? And then let alone doing the right scaling and doing the storytelling in an automated way as well, where you add something like a title. That's even the next step after that. I'm heard there's companies now trying to figure it out, but I think we're not quite there yet. And it's as long as this stands, then we have this task of actually doing that, and doing that in a way where we're making responsible decisions and not choosing the wrong graph, or not kind of biasing our data in a way that the graph's actually misleading, right? So we are faced with that. And then finally, we also have to test if the graph represents information correctly, right? So, and then you have that narrative on top of that, as I just said, right? So oftentimes, actually, that's a key thing here I'd like to mention, actually, is that add a headline to your graph that's descriptive, that's actually descriptive of your story, right? It was mentioned yesterday by Isaac Reyes too. Again, I'm still very impressed by the presentation, right? But it's really go the extra mile to not just describe what's shown on the x-axis and the y-axis and but actually tell a story around what's going on in the graph, such as, one curve is 3x the amount of the other curve, and then maybe even have some form of discussion. Try to keep it quantitative is my recommendation. Maybe the discussion really depends on the audience, but headlines really go a long way, such as in many other media as well. If you do PowerPoint presentations, you publish articles, you write books, you also give talks. The headline is actually very key to having a good description of what's going on. All right, any questions at this point? Great, okay. So let's go on to some elements and tools. That's at a fairly high level. I think there's some really cool elements or some elements I really liked in the kind of what, why, and how of data visualization. So what is the most simple one, of course, where you really just look at your data and your data set types. I think for the most part, we're all sort of in the table space where we really have items and attributes and normally rows and columns and more rows and columns. Whereas there's also, of course, other data types, such as networks and trees, where aside from items and attributes, you also have links between the individual items and their attributes, right? So that one is as we're using, that one can actually be generated oftentimes by data visualization or by graphs, right? Where it's like you build a graph around your table and then you use that again as a new data set. You have fields, and those can be maps, for example. You normally have grids of positions with the attributes, and you have geometry, and you can also just have cluster sets or lists. That's where it gets more towards. What's a good example for cluster sets and lists? It's very popular right now. Very popular to be analyzed. Any idea? It's everywhere. Quick hint. What's that? No, it's not a plot. We're talking about, data and data set types. So these are actually just sets, and this can be any unstructured data, right? So text data, images, maybe not images, but so text. I would say text data and mostly text, right? Images would be in the field here probably, right? Or in your table data, depending how you translate it. But so these are different data representations. Basically of your underlying truth or your underlying information, right, that you're trying to show. So that's the what. It's fairly abstract. You go to the why, it gets a little bit more interesting. That's where you now start relating your different data, right? So, for example, if you look at the query here, you're just saying, well, if we plot two columns of our data, if we plot two columns of our data, we can just say, well, we find certain points around that plot, and they're somewhat interesting to us, and therefore we have succeeded in our visualization at a very high level, right? We can also compare two different curves. We can do that really with any two different graphs that have basically fixed axes and fixed design elements side by side or top bottom. You can also just summarize by highlighting different elements, say in a table view and a grid view. And then in the search side of things here, I think that's actually a pretty cool example of showing kind of a 2x2 matrix of a search problem where it's you either have your location known and your target known. That's also known as a lookup table. That's basically where you have perfect information on. A lookup table can actually be a model also, where you know where your targets are and you know what location they correspond to. Locations can really also be variables here. Any type of variable. It doesn't have to be geography, right? So you just use a lookup table to say, okay, I know where my targets are. If you give me a location, I can definitely tell you what targets are to be found there, right? Now, if your target is not known, I can actually do some browsing through locations. So that would be the case in the top right. And if your location is not known, on the other hand, and your target is known, you can look through all your targets and try to locate them. And then finally, you have the case of where both your location and your target is unknown. That's where you really get more to the exploratory analysis side of things. Another case of why there's more things that can be done with data visualization. They can simply be consumed, where you try to discover things, where you try to present them again in, say, network graphs or bar charts, or where you simply enjoy them. You can also produce things where you tag and label things. You can then also record. That's basically just that's basically connecting different type of data elements here, and you can also derive. Derivation actually is saying, okay, you have two columns, you combine them into a new one, and then say you visualize that, right? So what are some of that's kind of the why, some of the use cases for why we do visualization, right, on abstract level. At the how level, or what are some of those visualization tools that we've all seen, right? So these are very, very simple, or I would say, the most widely used visualization tools. This is actually a report from, I think I found on visual.ly, and it's kind of showing your histograms, the bar charts, bubble charts, radar charts, waterfall charts, right? So it's and all their use cases in a way, and I think that's really the most widely used ones, because they're all 2D, and they're all, some of them come from stats, others come from more modeling, computer science community of things. There's also the pie chart. I think pie chart got quite some bashing yesterday. in the presentation for those of you who were there at Isaac Ray's presentation, just because it's really hard to actually compare different elements, compare the size of different elements with it. It's normally a lot easier on a bar chart. However, you have to say actually this pie chart, if your sizes of your pie slices are fairly different in size, it's actually rather effective of doing that, right? If on the other hand you have a very similar size of slices or size of data elements in that pie chart, it might be much harder to do so, right? So in this case, actually, it works pretty well. And then, of course, there's other things where pie charts were kind of projected into 3D, and it becomes even a lot harder to see those, to see the relative sizes of those elements, right? I have another example here that I thought was great. What has been done with these type of, say, time series or line charts. Very simple line chart here, for example. This is a time series example of 250 years of sunspots data. Is everyone familiar with the sunspot? I think it's a fairly famous machine learning data set, actually. Anyone wants to explain what a sunspot is? Yeah, it's just a dark area in the sun, right? That is significantly cooler than the rest of the surrounding area, therefore it appears dark to us. Yeah, go ahead.
It's important to know the sunspot because it's also connected with the plasma that is shooting to the Earth.
Yes.
That's the reason
yes.
Yes,
and there's a certain periodicity to it, right? So if you look at that graph, what can you tell me about sunspots? Can anyone? It's a bad graph, right? It's kind of like one of those D- charts that we saw yesterday. So it's not, and you can actually apply a fairly simple stretch transformation here that then lets you see a lot better what's going on, right? And you can kind of see this periodicity of 11 years, where it's like you have around 5 peaks in every 50-year block there, right? So that's a fairly antiquated example of like turning an okay graph into a better graph, right? Where it's a really busy graph that is very dense and has a lot of information and is hard to discern what's going on. And just by actually stretching your y-axis and compressing stretching your x-axis and compressing your y-axis, you have this effect where you see now out of a sudden the periodicity a lot better, and you can discern those trends, those seasonalities that are going on, where it's every 11 years or so you have a peak, but you also actually see some trends where we have certain decades that are lower in magnitude than others, right? So you have a much clearer picture by applying simple stretch transformation. So I'm going to elaborate a little bit on those like visual design aspects that were kind of mentioned in my abstract as well, where it's really we should really focus on showing the data, right? That's the main thing, where it's like you don't want your graph actually to abstract your data in a way that the data is not very clearly visible anymore, right? That it's kind of converting it into something weird that's not representing the data very well. There's also the data ink ratio concept, which is talking about you want to present many numbers in a small space, where it's saying use the least amount of ink to show the maximum amount of data, right? So you're trying to be close to 1 in that data ink ratio. What are some other good ones here that we just saw? You want to give a great description, exploration, a clear purpose with it. You want to describe a problem, explore a data set, you want to tabulate or decorate, right? Several levels of detail. And as we just saw, you want to see relative sizes of elements in your data visualization, right? So Tufte is kind of one of the thought leaders in this field I haven't talked about yet. Yeah, please, go ahead. For this particular talk, they will be afterwards, I think. That's what, yes, we upload them and then they will be distributed. Any other questions? Okay. Yeah, so these are very well-established design aspects, visual design aspects established by Edward Tufte. He has a series of books on that. One of them is the visual display of quantitative information. There's also one that's called envisioning information. I encourage you to check those out. If you get a chance, they have great examples in them, as I said. We really talk about things also like cognitive load, where it's like how how many elements can you actually consume in a graph, right? So how many dimensions we're used to navigating in a 3D environment, right? So the assumption is we can't actually consume many more dimensions on a visual canvas either, right? Again, even though people are actually trying to compress more dimensions into one graph. That's one aspect, the cognitive load side of things. Data ink ratio is a great one to actually keep remembering yourself. It was mentioned yesterday that grid charts and the grid lines can help you for like navigating your eye through a graph, but they can also actually add additional ink that is actually redundant in a way. So one recommendation was to say, let's not use grid lines and actually text annotations at the same time, because you're really using more ink than you need to. Other considerations on that is, who's the audience? And I think context has to be applied here. Are you talking to executive audience? Are you talking to the general public? Are you talking to your friend at a cocktail party? It depends, right? So it can really be actually quite different how you choose your chart. What is your target medium is also something that's easy forgotten, I think. Are you showing your graph actually on a laptop, or are you using it for a presentation on a large projector? Are you trying to print it on a poster maybe, or in a magazine, or in a journal? There can be quite some optimization that can be done in terms of resolution, color depth, format. Are you using vector output format or using raster output format, right? Depends a lot on your application. All right. So let's show some more graphs and this is called advanced graphs in R, but it's really advanced graphs that could also be implemented in Python in some of the libraries that are available there, for example, Seaborn or Bokeh. We have some, so the graphs I'm showing now actually in this next section, they should be a little bit more exciting than what we've seen so far, although they might also still be familiar to you. But I have code provided, or there's code on my GitHub actually, that we will be able to work with after that, that you can actually render those graphs yourself and play with them a little and maybe use your own data set to use them, right? Or to make them your own, let's say, right? So let's call this beyond line charts, scatter plots, and histograms. There's really tons of reference. I'm just picking 3 here, which is our graph gallery, great. There's flowing data. There's a shiny gallery on Plotly. And I really just want to highlight 4 or 5 of my favorite, this is a very biased selection of advanced / complex graphs. They're my own personal favorite, but I think they all have their use. They all have in common that they're a lot more advanced than, say, a simple bar chart or a line chart or a scatter plot. So beware that it's not just because they look great or they're very visually appealing, it doesn't mean they're always the right application. Oftentimes they would be overcomplicating things, and bar chart or line chart or just scatter plot could be the best thing to use, right? But these are great, I think, if you really have a more complicated task at hand, if you have many dimensions, if you have things where your data changes over time, or you need interactivity to actually explore that, right? So a lot of the ones I'm going to show actually support interactivity, which is great. Unfortunately, I'm showing most of them in a static way here in this PowerPoint at least, but once we jump into R later, we can also look at some of that interactivity. So first one will be the stream graph. Sorry, there's a little bit of a lag here. So that one, some of you might have seen that. The stream graph is actually some form of layered, not a layered bar chart, but a layered chart, but actually like a layered bar chart that is closed all the way to 100%, right? But it's really great for showing many entities that fluctuate heavily over time, right? So it's not always useful to discern different sizes of different streams with respect to each other here, but it's really great if you have a long time series, say from like 1950 to 2010, and there's really a lot of elements that are changing over time, such as here, for example, this is a project from Google on music timelines where it shows the progression of different musical genres from the 50s all the way to now, and it shows, well, it was dominated by, say, like jazz in a very heavily majority type of way, but then jazz really faded all the way out, and really by the time you hit like the 80s or 90s, you don't even care so much anymore about the relative size of jazz, because other genres such as pop, rock, and then also metal and other genres later on have actually taken over by then, right? So it's really great. You really have more. I think there's this kind of magical constant in the stream graph where it's like, well, at least you should have 6 elements or more, so it makes sense, right? So don't use this as we only have 3 elements, because you're probably going to get shot for it, right? So this is good for having lots of elements and that change really heavily over time, right? And then the cool thing, of course, with this is that if you go to the link that I'm providing here in lower left corner, again, sites will probably be shared after this by the organizers, you can actually apply all sorts of interactivity, right? You can hover and explore the individual music streams, or you can also just enter your artist of choice and track his progression through this chart in a way, right? So great things that can be done with that. Again, holds a lot of data in the background, obviously, and it's not something that you do over a cup of coffee. Or maybe we are close to doing that, actually, right? Second one will be the sunburst chart, or how to tell the difference between 66 sorts of cheese in that particular case. So again, large amount of detail being shown, but also in this case you have more of a multiple level structure, like more of a hierarchical setup where you start from basically the type of milk that you're starting to make your cheese with. So you have cow milk, goat milk, sheep milk, and so on and so forth, and then you actually go to the second type of hierarchy as well as a hard cheese or a soft cheese, and then all the variations in between that, right? And then you go all the way around to individual, say, like cheese labels or names, right? So that's a great one too, I think. Again, sources being provided over here. There's a Sankey chart next. That one is basically a special case of a flow graph, so also called alluvial chart sometimes. In this particular case, it's called My Monthly Energy Bill Redesigned. So that's just saying, well, here's my bill in terms of dollars on the left-hand side, right? This is electricity cost in dollars and maybe gas cost in dollars, and then it's kind of tracking in some stylized way actually to, on the right-hand side, it's a little bit small here in text. I don't know if you can all read that, but it's talking about, okay, how much of my bill is actually from heating, how much is from lighting, how much is from food storage, how much from cooking, and so on and so forth, right? So it tracks it to individual elements of those cost buckets, right? There's actually one problem here, something that was pointed out as a weakness for this graph, which is saying that, well, heating, so both of those right-hand side arrivals of those flows actually say heatings, both the first one and the second. So this is the gas part of the heating, and this is the electricity part of the heating. So actually you have 44% of your entire cost being due to heating, but you're really splitting it up into 2 because of the different nature of the energy source that you're using for the heating, right? So even that might not be the best chart to show here, and you might just be actually better off with a bar chart. Again, keep that in mind, but I think it's a great chart to track a lot of elements and have sort of a hierarchical breakdown of bigger buckets into smaller buckets. Finally, that's one of my favorites. It's the circular plot or chord diagram. There's a lot going on here. I have no idea what. It's used a lot in genomics. I will show a better example in a second, that way you understand it a bit better. This is just, I think, where it gets really, if you're a scientist and you look at this, if you're a genome researcher, right, you look at this all day in your lab, you will maybe have a pretty good idea what's going on. For us, it's never going to happen, right? But I think it still has some use that I will show, but I think also there's this interactivity can be key here again. As with any of those 4 charts that I was showing, interactivity can really be a great element to explore that a little bit better. Again, show a lot of detail. So I looked at another example of that can be done in R, which we will also look at later, where you can actually tell a better story around it, and where you actually say, well, okay, this is a circular plot again, or chord diagram, and you're now looking actually at migration patterns between different countries in Southeast Asia, right? So including Malaysia, Thailand, Japan, China, India, and Australia, and you're really showing, well, what migration is actually going on from those countries. So the outbound flow is highlighted here with those second ring layers. So this is all the outbound migration that's happening from Japan. For example, you can see there's outbound migration from Japan predominantly to Australia, and then also a little bit to Thailand, but that's pretty much it, right? And then on the incoming side is in this remaining area here, you can see a lot of the migration to Japan was yellow, therefore it came from China, right? So you're really showing inbound and outbound flows at the same time. It looks a little busy, but if you pick one country at a time, and compare it to one another, you might actually be able to discern the patterns here a little bit easier than on a map. And the reason for this is you basically have a fixed reference, right? And you're not distracted by oceans and other elements that happen to be on a geographic map, right? And I also provide the underlying data set here just as a reference, so you can kind of see that example again, right? So you have this is kind of the source country where your flow starts from, your outbound flow. Again, this is, for example, Japan has the biggest migration to Australia, 180,000. This big green arrow here that I was showing, and then the other countries are really slower, smaller. There's a little bit to Thailand, and the rest is really largely insignificant. So that's great to actually have show a good amount of data. And the other thing with that, of course, it's a lot more catchy than a bar chart oftentimes. It can be a lot more encouraging for actually someone maybe that is not so used at looking at bar charts to see this and look at it more from artistic side of things and say, well, this is pretty interesting. What the heck is going on? I'm now going to spend some time trying to understand that, right? I think that's really what one potential power of data visualization is. We can really encourage our viewers or encourage our audience to look at the data or look at whatever we produce, right? Was there a question in the back? Yeah, please. Sorry, it's a little slow. I repeat the question, but I can't even, it doesn't even get here. Please, if you don't mind walking up. Sorry, I think so. The question is, I'm not quite sure if I understood the question, right? But I think the question is, there is some overlap between the 4 chart types that I've shown? Yes. That's right. It's a good question. No, it's a good question, definitely. I think I alluded to that in my introduction, actually. It's not solved in a deterministic, analytical way, I would say, right? It's definitely biased by the person who prepares the chart. You can get feedback, maybe. You could have a majority vote. You could have a survey, right? You could crowdsource the information on it somehow. That's actually a good way of doing it. I think that was done in a couple of presentations yesterday as well, where the presenter asked, okay, is this the best chart, or is that the best chart, or is this your answer, or that your answer? So you could do that, but unfortunately, there's no deterministic way to do that. Right now, and that we have really this, that was also a point I made earlier, we have this wide range of tools and templates and graphs to choose from every time, and it's actually one problem that we're facing, and one problem why bad graphs are being generated a lot, right? Or why oftentimes data is maybe not shown correct way in a graph, because your software presented a lot of different possibilities to you to start with. Does it make sense? Okay, good. So those are 4 that are fairly similar. Now, I do have one on reserve here that is fairly different from the other 4. It's actually one of my personal graphs, or not personal graphs, but from my PhD work, where we look at the time series. There's a lot going on here. Maybe we'll spend a couple of minutes or so to explain. These are actually 3 years of CO2 flux data, where it's called a fingerprint. In a way that you have 3 years of data, and I'll explain to you what the data actually means in a minute, but the key thing here is you take your 3 years of fingerprint and you actually kind of warp it or cast it onto 2 time dimensions, being you have your months on the x-axis and then you have your hours on the y-axis, and out of a sudden you see like a spatial-temporal pattern, let's say, of your ecosystem activity, which kind of looks like a fingerprint, which is really nothing but saying, well, your ecosystem activity varies by season, but then also by time of day, right? So it varies by both dimensions and creates those type of fingerprint plots where during daytime, so middle of y-axis here, and during midsummer months, so for example, July of 2007, July of 2008, you have the biggest ecosystem uptake in terms of photosynthesis, for example, plants taking carbon up, plants sequestering carbon instead of releasing carbon through respiration during other times of the year, predominantly during winter and also during nighttime, right? So you can show a lot of complexity. You can show with those 2 time dimensions, out of a sudden you can add a lot more context, right? You're basically discretizing your data is already discrete in that sense, but you're basically conceptualizing your time dimension here into two different, you're splitting it up into two different axes, and then all of a sudden you have a much more compelling story than just showing one of those high frequency line charts. This is underlying, this is actually very high frequency data, it's 10 hertz of data that normally gets aggregated into half-hourly data, right? So then half-hourly is for 1 year, you still have around 17,000 data points. So doing this kind of trick where you say, let's use months and hours as axis, you can get actually much more compelling visual. And on top of that, there's even more going on that's interesting for us from data science standpoint, actually, where you say, well, I'm also, aside from that, I'm actually going to map my 3-year ecosystem flux plot on a data coverage map where it's all the white things are actually gaps or missing data, right? So that was a project for doing a data imputation or data gap filling with artificial neural networks. So in all the white areas, you would actually use your artificial neural networks to impute the data. There's even another detail here that's showing gray versus black. That's kind of a data quality indicator that's also captured in that. So black areas would be data of high quality, whereas gray data would be areas of medium quality or not so good quality, right? So again, a lot going on, might be a lot to digest if you're not used to looking at these type of graphs, but as you can see, I just spent a minute or so to actually explain it. So that's another story, I think, or that's another point about data storytelling is if you have a graph like that, if you're in a presentation or if you're actually trying to explain it to someone, take your time to explain it and actually explain the individual elements. I probably did an okay job now, probably not the best one, and there's a lot going on, but take your time to actually do that because otherwise then you're creating this type of confusion or you're creating actually too complex information. If you're not, that can just basically be distracting or basically frustrating to your audience. But with that, I would say, any questions on that graph? Any on the statistical element? That's also done in R. Don't have the code up on that one in the GitHub. But if you're interested in making that graph, it's just using heat map. I think you might be familiar with heat map function and doing some warps around that. All right, great. So to sum this area up, we have a trade-off. Yeah, so advanced graphs, not just in R, advanced graphs in general. I think we have the trade-off between showing enough detail and then also the cognitive load that Tufti mentioned, right? Where it's really, how do we balance that? That's really one of our tasks, I think, as data scientists or as visual information engineers, let's say. How do we balance that showing enough so it makes sense, it has a story, but not overwhelming your audience at the same time, right? Secondly, we have there's a tendency going on where we want to, at least in those examples that I showed, that we want to show more complex information and more dimensions. I mentioned some of these things already. Let's actually skip over that. So you have the crafting and take your time to tell the story. I just mentioned that. Great. So emerging data visualizations, there's some more examples that I have here around what I think the future holds up for us, but I think we're almost on time for the exercises. Great. So emerging data viz. So I have an example that I saw earlier this summer where I just stumbled upon the Science magazine that is looking at what is tomorrow's Earth going to look like. It's not really specifying when tomorrow is going to be. But one thing I picked up on that is that it's that there's a lot of graphs on there and a lot of data viz on there. I was kind of excited to see that. Obviously, so there's really a lot of your speedometer there, and then you have your kind of I don't know if that's kind of like a solar panel that is indicating how much it's being charged right now. It has been charged over the last years or last few days or so. And then you have your performance chart there in the middle, another speedometer. I really don't know what the Science magazine thought about all these speedometers here. Apparently, they're really. I've seen them in some machine learning software too recently. So they're really popular type of graph. Maybe I should have spent some more time talking about those. Or we can find an example actually in R or Python later. But what I'm seeing here is really tomorrow's Earth will actually be more quantitative because for graphs you need quantitative data, right? And I think more digital, as we all know and as we all hear all day. But then I think therefore, which is the key message of this graph, is I think it will also be more visual, right? All right, so to wrap this up, let's look at a couple more graphs that have gone around the world and that some of you might be familiar with already, but I'm going to show them anyways. This is 10 million of data points in one large network graph. Facebook, yeah, again, based on more than 10 million data points. Normally, that's great if you see that map first. It's it offers a new way to look at the map of the Earth, right? Where it's really before you maybe look at climate zones or you look at kind of pollution or urbanization, but this out of a sudden now explained to us social media on a global level, which was really kind of like an eye-opening synthesis. It takes only 10 million of data points and maybe 3, 4, I don't know, 5 years of Facebook activity. So really something you can't just generate without that data. So great example of how visualization actually opens our eyes in terms of how biased actually social media are or were at this point towards the Western world or towards Northern Hemisphere, really. Okay, so finally I want to touch on some points. How do you actually test if your graph represents the data correctly? So if you have something like that, if you have 10 million data points, how do you get an idea of if that's actually representing, is that's right? Or maybe there's maybe not a lot of other users that we're actually missing somehow in other countries, let's say. How do you validate that? You guys got any ideas? What do you normally do? You have any big data visualization engineers in here? People shaking their head. Don't be shy, it's fine. 1 million data pairs counts. It doesn't have to be 10 million. What? Yes. So taking more samples from it, right, and looking at basically sanity checks or validation checks. So it's called a QA. A lot. So I've given some QA recommendations here. Multiple samples, right? Take more samples. It's a fairly simple one. Don't just produce your graph and run away with it, because you can actually easily have missed a point or you have an error on your code or something and you're showing something wrong, and this can be very embarrassing later on when you have to defend your analysis for some stakeholders, right? Various aggregation levels are always great. Can you actually aggregate to, say, country sums and do they check out, right? Or to country means. You can do a simple group bias. I think we have all the libraries in the world that we need now to do that. We have the dplyr data table packages in R. We have a lot of libraries in Python as well for that. And again, plot even more samples, right? So samples are really the big deal. I'm repeating that here just because I think it's important. Number 4, very important also, validate with other data, right? So maybe for that Facebook map that we just looked at, what other data could you validate that with? There's other data you could look at, right? What for example? Maybe another, yeah, that's right, just another social media. Or maybe even something like population, right? Like a population map, very simple. Of course, we will not get some of the nuances of social media social media data, but you could at least look at, okay, is there a significant number of population to even have that actually is an upper boundary of that social media counts, right? So things like that. You bring another data set and you all of a sudden your analysis or your risk can get a lot more powerful. Use interactivity, of course. That's another way of not having to pull more samples and actually just visually exploring what exactly is going on. And basically doing a visual validation in a live fashion. Then next you also can look at visual significance where, okay, that doesn't really apply to that last map, but you can graph your uncertainty, right? Where that's more on the representation side of things, where if you craft a specific story, sometimes it's actually important to check if you use the right kind of ranges and scaling and to not just, if you zoomed in too much into your scales, oftentimes you can see like artificial differences that are not actually different at all if you apply like some statistical tests or you add uncertainty measures to it, right? So that's a good one. You can do transformation of axes. I think I've shown some of those examples before. Okay. So finally, to wrap up the talk part of this session is, what will graphs look in 5 to 10 years? Just thinking, going from where we just went kind of like old school or widely used histograms, bar charts, to more advanced 2D charts, to things like maps and 3D interactivity. There's a work here that stood out to me. It's called the 5D colorimetric technique. It's also used in neuroscience. So we can really, it seems like as data science practitioners throughout industries, throughout many different industries, we can borrow a lot from from genomics and from neuroscience, because they have this task of, mapping many different dimensions, mapping the brain, which is 3D first. You normally have a time dimension too, and you show other processes or other attributes, you add another dimension. That's why they arrive at 5D here. I still think it's hard, so be aware of that. There's a caveat here, of course, that your audience might not be able to process much more than 3 dimensions at a time. They might be really overwhelmed. And for example, this is really just a 2D graph, so they're making it 5D by saying, well, we're mapping it on this 3D structure of the brain, right? But definitely things to, and you can get this rainbow effect there too that we were talking about, where it's like it's actually too many colors to see anything. But again, if you add the interactivity and you're a domain expert, you might be able to actually use this graph and maybe then also apply it to something else. Finally, I think I was very impressed by, or not really aware so much yet of this particular visualization that was shown yesterday in Andrej Karpathy's keynote. So this is a visualization, right? It wasn't quite clear to me when I saw it first, but I looked it up a little bit yesterday for a few minutes. So a visualization of a computational graph of 18 million vertices and 115.8 million edges. So add those 2 data pairs together, much more than the 10 million Facebook nodes we just saw, right? So that's crazy. So that's using a good amount of abstraction, of course, to show these type of what's called IPUs, intelligent processing units. So it's saying, well, nodes are really within those intelligent processing units. And then the connectivity between those are the graphs. I have a hard time seeing it myself, to be honest, but it's really intriguing to think about using visualization as a means to show the most complicated neural network, or very complicated neural network that's, for example, used in driverless cars or in other type of automated machine learning applications, like we've seen yesterday, the software 2.0 example, right, where it's neural networks generating software 2.0, and then we're trying to, we as humans, we generate the software 1.0, we're trying to catch up, or we're trying to see the intrinsic differences, where visualization can actually help us to look at that in a more augmented view, right? Great. So with that, any more questions? So for the takeaway, there's a few points I summarized for you here. Data visualization is highly interdisciplinary. It's not quite as simple as we might think. I think data visualization needs are ubiquitous along data science stack. We've seen that, not just in the descriptive layer, but also in predictive layer and semantic layer, getting your results all the way delivered. Data visualization is not fully automated at all. Picking the right graph, picking the right template, doing a good job in that is not automated, so it's up to us to do it, and it's up to us to check if we're actually following Tufte's design principles and basic visual design checks, such as data inc ratio, right? And I think I've shown some new techniques to offer a way to pack even more data into a graph, but those normally come at a cost, so be aware of that. It can take a lot of time. It can take a lot of heavy manual editing and tagging and making sure it's actually readable at all. You should take time for detailed descriptions if it's in written text or if it's in communicating to your audience. And you keep in mind the danger of cognitive overload. I think we've also seen some examples of cognitive overload today. And finally, my closing note is I think learning how to make better visualizations and to fit visualizations to any given data set can actually help us to improve our means of visual communication. All right. So with that, I have some more references here that I mentioned, just very more on like a book chapter level, right? Menzer, Tufte, and Wilkinson that I'd like to highlight. But with that, I take more questions. And then we'll go to the exercise in a few minutes. All right, any questions on the material? Okay, that's good. Yeah, please.
Any other books you would recommend in addition to these 3 that you used in your slide? For data visualization.
As I said, there's a few other ones from Tufte, envisioning information. There's a quantitative display of information. So Wilkinson is a good one. Wilkinson is actually, Leland Wilkinson is the author of ggplot2 package from R. Then Tamara Menzer, those are my 3 personal favorites, I would say. Yeah, there's some maybe on graph theory as well that has good visualizations, but there's many other ones in the literature that that you can. I can send you a longer list of literature that I have in my library at home. Yeah. Please.
You have shared three links. One is graph gallery and flowing data and something like that.
Mm-hmm.
The main is R. Do you have any link for Python and similar? I look at those links very cool. Similar.
Yeah, I can share with you. Okay. Good. Okay, so let's go to the R exercises. Any more questions before I move on? Okay. So there's two different exercises we can go to. So first of all, please see if you can navigate to my GitHub. So if you just go to github.com, Olaf Menzer, and then just actually, you don't have to type out the Biopharma app even. You can just jump directly to the GitHub. And so we have two exercises, by the way. One of them would be for a biopharmaceutical app, which has interactivity for sort of a visual clustering. And this is built in RShiny. And it basically uses some heat map plotting, hierarchical clustering algorithm, and then also a phylogenetic tree to visualize some of the clusters. So that one I will go through in the code. And the second one will be complex graphs in R, which will be the four examples that I was showing, stream graph. And we can look at that in a minute, right? But basically those main four advanced graphs I was showing, we can also play with that a little bit more. I'll be here to answer your questions as well. Yeah, so why don't we give it a shot to boot up your R Studio and to navigate to that link. I'll come around. It'll take a few minutes to get the setup. Yeah, so if you just go to GitHub actually and then search for my name, Olaf Menzer, O-L-A-F and M-E-N-Z, or you should be able to find it. There's not a lot of repositories either. So the Biopharma app will be the first one. It actually has a pretty comprehensive README. So for those of you who are already there, who are already bored, you can kind of get started on the README. Those biopharmaceutical app is actually an app I have that has been designed for this tutorial or for this workshop in collaboration with one of my colleagues at a big biopharmaceutical conference, a big biopharmaceutical company in Germany. So he was actually, his name is Sebastian Wolf. He was recently invited to give a talk at Harvard on what he calls the biggest Shiny app. So he's doing RShiny all day, and he can do it a lot better than I can. So we've actually sat together here and developed this mini example of a RShiny app. And I mean, while you get started getting into this tutorial, it's at 35% of collecting my error info. While I'm doing that, I can talk about the app a little bit. So the basic idea is, I mean, the first thing that why we're doing Shiny is, I think, because it's such a great tool to actually have a user interface or have a GUI up with a few lines of code. So you really only need a couple of R functions, right? One UI function that's a user interface, and then one server function. And with those two, you're pretty much good to go. And you can basically have empty code in there. Just add a couple slider elements, and you're good to go. So if you use your local host as a server, you're really only one package away from hosting your little mini GUI, right? And having basically sort of like a sender app and a listener app, or a sender function and listener function in terms of server function and UI function. So if there's two different, so if you go to the app.r in that biopharma, I'll show it on the screen in a minute. If you get lost, don't worry. But if you go to the app.r, it's basically just showing you that empty framework of a Shiny app, right? So no matter what the application is, you can actually use that app.r function that we have provided in there, which is very simple, Shiny R example, but you can put any type of visual app or dashboard around that, right? You can build any type of visual dashboard or visual graph, interactive graph based on that template function, right? So that's great. And then there's a finished app.r which is the actual app, and I'll go through some of the code to show how that works, how you got there. But even that doesn't have a lot of code in it. So it's still a fairly lightweight app with some good means of interactivity. All right. Let me just get up my R here as well. Yeah, so if you navigate to the GitHub page, all right, finally coming back on. You will see the biopharma app, right? And basically what I was describing earlier, kind of hand wavy without a screen, is that there's a README that's nice, but the main things are there's an app.r and a finished app.r. So the app.r is really just your an empty tutorial app, right? That's really basically your almost like your minimum working sample for your R Shiny that you can turn into any other graph after the fact. Let me actually change our monitor settings here once again. Cool. So app.r, let's bring that up in RStudio here. And everyone else who is not in RStudio yet? Okay. By the way, I wish I would have this hosted in a notebook environment somewhere. It's definitely, this is my first time at ODSC too, so if I come back then we'll have everything running in a notebook. I think it's a lot more suitable for having this type of demos or workshops. I've seen some great examples this week. RStudio is a little antiquated to do that, but it'll do the job. So anyone not in RStudio yet? Okay. Good. All right, so the app.r, again, I was describing, right? So all you really need is Shiny. There's also Varieties Lite. Varieties Lite is for visually impaired. It's for using better color schemes for visually impaired folks. So that's the other library. It's not really required for having Shiny app, of course, but it happens to be in here because it's almost minimum, right? It's not quite full minimum working example, but really all you have is you have kind of your UI. It uses a fluid page here and has some kind of style sheet, CSS definitions first, but what you're doing is you have a sidebar layout, sidebar panel. Why don't we just bring it up? So that's basically a minimum app. You can just do run app. So that might not work for all of you immediately. Has everyone tried to click the run app button? It worked for everyone? Anyone not working? There's one issue there? Okay. I'll come around in a second. But in the interest of time, we'll proceed for now. So this is basically a simple Shiny app that has a slider here for your number of patients and your number of clusters. And then also for your clustering method, and then kind of the task of this tutorial is basically to fill in those heat maps and the clustering output, right? So, but again, the task at hand was actually, to give a little background on that, is basically you take some measurements on your patients that have a tumor, and you're trying to figure out if the tumor is malignant or benign, right? And you take a series of measurements, and one goal for the biopharmaceutical company was to actually take less measurements, ideally, and therefore save costs, because they have to run this they have to actually perform this analysis on a lot of different patients. But to also understand, of course, which different features in your data or which different measurements can actually be a good indicator for someone having a malignant tumor or not, right? So obviously that varies also with the number of clusters. Clustering can be used to solve that problem, right? So we'll see in a minute how that works. But again, from Shiny app visualization standpoint, you basically just create your elements here with the given apps that already exist in Shiny. You have a sidebar layout, and then within that, you have a sidebar with your custom input, your two sliders, right? One of them for the patients, one of them for a number of clusters. You provide these are actually hard-coded here, right? It's not ideal, but for this example, it works. Ideally, you could parameterize that better, but you really say, okay, we have between 10 and 100 patients that we need to run this with. We can't really run it with less than 10 patients. We're starting with 50 as the default value. And then you have your input also for your different clustering methods, and then those are just, so select input is basically just a drop down, right? So if you go back here to the app, It's really just a drop down, and it uses the select function to kind of propagate that to the h-class function, or we will use that actually to put it into the h-class function. Okay, anyone else that has issues running the app? Or? Okay, I'll check real quick. Yeah. I wish I had a tech support guy here too. I've seen sessions this week with one guy presenting one tech support. That'd be great. Okay.
There's a utility of file you have there.
Yes.
You have to download that also?
Yes, you want to download the. Yes, sorry, that's a good point. So you want to download the entire repository, right? Not just the app.r file. Okay, so one potential error here could be folks only downloading the app.r. That will not do it, right? So try to get the util file. I think it's in here, right? The utils.r. So get that file as well. That's a good point. So without that, it won't run. That could be a potential error. Any other errors folks are getting? Can do some live debugging here. Yeah.
I just ignore this one. There's an error in heat map. It's warning.
If it's a warning, then
But it also
you're
say app.
fine. Are you running app or
No, I was.
did the app come up? Yeah. So please, by the way, as I'm going around helping folks here, for the others that are getting bored, just keep working your way through. The tutorial is pretty much DIY, but I'll keep going through it, see how far we can get. But this is you in the finished app already, right?
Yeah.
Did you try the normal app?
The normal app. So do I have to close only one time?
You can only have one app at a time, yes, but in this environment. Mm-hmm. I will talk about that actually. That's a good question. I haven't talked about that yet. Let me add a couple notes on that. On the deployment side of things, of those type of apps. I haven't talked about that yet, yes? Yeah.
A few days ago, one instructor told me the name should be UI.R or server.R and cannot be anything else. So how did you deal with this trick? It looks like that works, right?
It might be through the utils.r if you check that, but I don't think it has.
Yes, he mentioned it must be Ellen. Shall we do it?
It might be for better compatibility with other type of package, but I don't think it's enforced. It might be mapped through this. If you check, you can check that file. But it's a good, yeah. There might be a mapping in there. Okay, and other questions? Okay. So are you running app.r or finished app? So app.r is yes. So again, there's two apps in there, right? App.r and finished app.r. App.r is basically the template with the tutorial is not done, and then finished app is the finished work. Only use that for your reference. So if you work your way through the tutorial, you can work through it similar like working through a notebook, just pasting in the code elements one by one or trying to go through them, understand them. I will keep doing that as we keep going. But the finished app, feel free to get a feel for the data already a little bit. I will actually explain that too, like what number of clusters, a number of patients, how they kind of relate. Okay, other questions? Sorry. That's interesting. You get that one. I wonder if you forked a different version of it. We got that one before, so that one is actually fixable with the. So the select input is actually select input is a function from plier, but I think it also exists in dplyr. So I think if you. That's okay. Maybe it's. It might be because you have a different version of plier, or so if you have existing RStudio distribution, sometimes there can be packing conflicts. So I can let me.
I can check for the.
If you go to the code, I can fix that for you. I think it has a. So if you do Control F for select, check if it's enforcing. So we can enforce if functions exist in different packages. We can enforce them with the package name : right? So the select input is actually exists both, I think, in plier and dplyr, and in this case we have to force to plier. Can you look to the next? Just click on next a few times. Yeah. Okay. Again. Yeah. Select input. Okay. Keep going. There you go. It's dplyr. Okay. Remove the dplyr : from both of those instances and try again. Okay. Other questions? Yes, so the package, that's right. So there could be some package miss. Which one? Macrid R, it didn't. It did. You didn't have that yet, or you need to update it. Okay. Yeah. So package versioning conflicts can happen, unfortunately. What it is? Yeah.
It's an error. If that one was true.
Okay. Yeah, so the thing is, installation of package ape had non-zero exit status. That means it actually didn't do it. It didn't complete even though you specified doing it. So normally this can happen sometimes if you have other dependencies that fail. Can you try again? It might have also failed because the Wi-Fi died or something. So can you just install packages ape again? Do that again. Let's go 2 up maybe. If it's still there. Yeah, if the package installations fail, just try to do it again. But there you go. Hang on. Moving. It seems like there's a language test. Huh. You have a, yeah. Darwin 3.4 C lang. That's kind of weird, yeah. I've not seen that error before. For some reason, you can't install the A package. If you Google this one, bin sh x86, this line with Darwin C lang, command not found, you might be. Yeah, that one. If you Google that and check, I haven't seen that. You got it. Okay, any other questions? Yes, we're adding those elements. Yeah, let me go back to, yes. You can do it. It's there in the finished app already, though, if you want to have a step at it. There's 2 different apps. Unfortunately, you can't run them side by side in this environment, but you can look at the finished app already and play with the actual task, yeah. Okay, how much time? We have about half an hour left, so I'll do a couple more minutes of questions, and I go back to run some more, show some more examples. But
I think I already have all of these.
okay, you got those before the session?
Yes.
That's nice, cool. Those are specifically for the app. You seem like you have a connection problem. UTIS R. Oh, you didn't download UTIS R. You need to get UTIS R2 from GitHub.
Oh, I thought I downloaded it.
Yes, maybe you download, but it has to be in a subdirectory R. Maybe you put in the wrong directory. Okay, other questions? I'll be right there, Catherine. Okay, let's do one here. All right. So,
Open the connection.
yeah, so some connection timeouts to.
Redirects the utils to the GitHub where I downloaded it. So that sources out fine, but.
So it doesn't need a download. Oh, that's odd. Yeah, okay. Let's source that one. No, what do you? Sorry, it's a little dark. Arrow cannot open.
Can't open a connection.
Did you just click on run app or did you source it?
I just sent it all.
Can you just save it and click on run app? Wait, what do you have? Yeah, so you have. It looks like you have some versioning conflict. Hang on, can you click on what did you say? Shiny is required. Yeah, so you have an old version of Shiny.
Okay.
0.14. So some of your you have to update your packages. For example, if you have a really old version of Shiny, it will not work.
Okay.
So if you just install Shiny again or run an update. Does that make sense?
Yeah.
Cool. You got it. All right, one more question over here, and then we'll go back to the demo.
Or we can talk
See?
about this after.
Yeah, they can. That's cool. Oh, you have those other examples too. Awesome.
Oh, the other one's
It's showing the wrong data. Yeah, it's normalizing it. Oh, sorry, I thought this was a wall.
And then it worked.
Okay.
And then I switched back to 3.5.1 and now it works.
Okay, interesting. Yeah, so versioning can be fun to do. All right, one more question, and I have to go back up. You got it, Catherine? Or? What's going on for you? Oh, you have it. Does the microphone still work? That's okay, though. People can hear the debugging. So you have your dplyr. Just go all the way down. What is the error say for dplayer? So dplayer wasn't updated or wasn't installed? Now go all the way down. So the problem is what you do if you close your, I don't know if you have an unfinished work, if you close your R session completely and then install your packages, it will work. Because right now it's not installing some of them because they're in use in another script. That can happen. Actually, RStudio has a way to detect that now, but sometimes still doesn't work. Okay, any other questions? I'm going to go back up and demo the app. Yes, empty screen. Okay, good. That's fine. Yeah, so app.r is an empty set of sliders. It's kind of like minimum working example. Okay, one more real quick. I gotta go back.
So does that mean when the is that because I think this is like just write a function to do the plot.
Mm-hmm.
So the reason we do that is because this one really takes
Yeah.
really long function and
Yeah.
put it here.
Mm-hmm. Yeah.
Is this the reason to do that?
It's kind of like a data prep. You mean? Yeah, I will talk about that in a second. Otherwise, we can catch up after. Okay, another one? Yeah. Is it working?
Not at all, because there is a problem with another library.
Yes.
And
It's being loaded.
UV.
You need a
Yeah, I tried to do it because it should be easy.
the dependency. Okay.
Should be, yes. If you go in
Do you have an old version of R? What's your R version? 3.4? Or maybe it's an old. It might be, yes. I think minimum requirement is 3.4, ideally, but it's. Can you check your R version? I think it's a check version.
I suppose they should be telling you also the rational.
Yeah, you have. Oh, yes. I think you just type version. No, check version, yes. Okay. Yeah. How's everyone doing with the app?
Could you slide that out? What are you doing?
Yeah, so let me walk through that a little bit. I haven't shown that yet. Okay. Everyone back? That's good. So who's running the app yet? The finished app? They're mostly working? Okay, that's good. So let's have a look at the finished app before more people are running out. So finished app, you just click on reload app. And you actually, let me see here. Oof.
So the number of patients, that's just sampled randomly?
Yeah, so you have a set of around 100 patients or so that you have that are shown on the heat map here on the x-axis, right? And as you can see, right now there's actually only 50 of them shown. You can increase the number of patients, and the heat map will re-render, right, and will add more patients. It shows you the 9 different measurements or 8 different measurements, right, that were taken for those patients. And you can actually recognize the 2 different clusters here already, where it's like those are the ones that don't have the symptom, and the other ones are the ones that have the symptom, right? And over here, you have actually the clustering result visualized in a tree map that also automatically updates, right? And it's a little bit hard to read on this side, but basically the purple circles are the benign tumors, and then the green circles are the malignant tumors, right? So as you can see, actually, there's a few that are getting misclassified. And I think the catch there is that some of them, the measurements might have gotten mixed up in the lab setting, right? Where it's like, it's actually the measurement of a different person. The clustering classifies them as benign, but or they're labeled as benign, but the clustering actually recognizes they're actually bad.
So they don't have any zooming kind of function?
That it could be added. This is a fairly thin, shiny app, but it could be added, yes. This is a little bit basically rescaling itself, but if you deploy this in a, if you can add the functionality. If you deploy in a browser, it will be a little bit better from zooming and zooming out perspective. This is just basically when you implement it, you show that in your Shiny app server. Yeah, go ahead.
It's also possible to create an interactive chart. If you click, for example, on a bar, then it highlights on another chart the same elements.
Sorry, you're saying if you have controls over here and then you have the chart updating in another? Yes. Yes.
And another chart.
Yeah. You click something and
These elements and show them.
if you connect them, yes. If you, I think so. Yeah. You forward them through. Yeah. If you make it an input of that function, I mean, it's all just nested functions, right? Yeah. So those are good questions. I want to actually talk about the deployment a little bit about that too, because that's a question I often get, and I actually also asked Sebastian that when we were working on the app, how they're treating that in that company. So for our Shiny, if you, let's say you build an application and you actually want to be able to deliver it to your users, how do you go about that with Shiny? Do you guys know about how it's normally being done? Yeah? Any?
Create your own profile on Shiny and then have like...
That's right. So you can go to shinyapps.io if you are a personal user of Shiny dashboards. And I think from what I understand, they're all public. So it's not, to an enterprise or professional setting, it's normally not what you can do from deployment standpoint, also from a bandwidth standpoint, I think. So there's a solution for it that our studio offers, I think, is Shiny Server Pro. But you don't have to go through that route. So I mean, Shiny and R is free, but then the hosting, of course, will still incur some costs in a way, right? You can outweigh that against other sort of dashboarding softwares. But I think one version to do it is basically to go through our Shiny Server Pro, where our studio hosts it for you. Or you actually just buy the software and host it on your on-prem solution, right? Or you just actually deploy yourself. I mean, you don't have to buy Shiny Server Pro to host it on your own on-prem, right? You either go to Shiny Server Pro and it's hosted on their side, or you run your own like Red Hat server and deploy it on there. Does that make sense? But the key, so you could run your own server, right, or your own virtual machine. So if you have access to virtual machines, if you're in a fairly large company where you have virtual machines, use one of those, right? Or you work with the IT department to get a server set up. So there is a little bit of a setup cost there, of course, right, in terms of like your time also that you spend. But the ultimate goal with this is you make it available in the browser. Like it will be available in the browser. The nice thing with Shiny is that you don't have licenses. You don't need like licenses headcounts, right? For other dashboarding software, for example, you normally need named licenses or named seats for each of your users. One advantage with Shiny is you just need to figure out how to deploy it, and it might be a little bit of a basic engineering process involved, or working with your data engineers closely. But I think it pays off in the long run. So the server is a compute resource, right? I'm not providing a server here. This is a minimum working example that's just running through our studio, right? That's just running on my physical laptop right now. If you want to take this app and deploy it in a wide setting, so people can access it through a browser, say an enterprise setting, then you have to go through a physical or through a virtual server that can actually host, right? Does that make sense?
No, what are the files that need to be on the server?
Those files, yes.
All these files.
Yes, you basically need to get a server. You need to install R, you need to install our Shiny and our Shiny server. And then you put your files and you should be pretty much good to go. Sorry? Well, I mean, you would run the app, would just be the app is you kick it off as a process and you forward it to some port, and then the port you call it in the browser, right? Yes. You mean executable that like as a file? Actually, that's actually a good question. I'm not sure if that's possible. You mean like a Windows executable or Linux or any OS or OS? You might be, if you can package it into an executable, maybe through Java, so just in a jar file. But
I saw a YouTube video of a lady who did it using Electron.
Okay.
And I don't know Electron other than I know Atom, that the text editor is written in Electron. So she teaches how to do that. She makes it sound like it's easy, but I didn't follow her.
Okay,
Yeah,
that's good.
You can sort of send just an executable to people.
All right, that's for like, yeah, if you want to share your work that way and maybe just developing a prototype with some collaborators, that might be a good way to do it. I think it's not so much used right now anymore in the digital age of cloud, but it's one way to port it, let's say. It depends on the size of your data also, because if you have a big data set, it's maybe not the most handy, because then you still need to link somehow to your underlying data. If you have a small data set, it's fine, but Yes, but then you have to download it every time. You still have to either save like a temp version of that file on the host machine that opens it, or you need to pull it and you need to have good internet connection, right? I mean, it's possible,
I
but
think the way she did it was it had no data.
right. Yes, it depends on the application. Yes. Yes. We have another question there. Or is related answer maybe? Or?
No, it's a different topic. I'd like you to talk a little bit more about the interaction with your client, because to what extent, like, the user is going to make this decision about the clustering method, or
yes.
about the variables to use, or even
it's
like the range of the number of patients.
Yes.
How was this approach and how we make this final recommendation for this model?
Yeah, so this is not, there's no final, so this is actually an interactive way to explore. So you're making a good point. This is not super stable from like, I mean, I look at this and I didn't build a specific data science, or the method behind that is something that biopharmaceutical research has shown to do, right? I'm not in that research right now, but it is somewhat, it doesn't, for this particular sample, it's a fairly small sample, it's not super robust, right? You can see that, for example. So again, question is, how was the design decision made for this type of algorithm and for this type of visualization, right? So, or for this type of decision making. My answer is it's not actually a fixed decision. There's no one set of parameters, and your parameters here are your number of patients, although you should really use as many as possible. Right, so the idea, of course, with data is if you only have 100 samples, I would prefer to use them all. Maybe have a holdout of 20% or so if you're early on the modeling process. But for sake of visualization, it's good to use the entire sample. So that's not even really a parameter. Main parameter here is your number of clusters. Currently, it's set to 2, and you can see actually you get pretty good clustering here in terms of purple area here and turquoise area here of different tumor conditions. Right, so it works fairly well. However, to the question's point, if you actually vary your parameter, your number of clusters, your results are jumping quite a bit, right? You add another cluster, third, fourth. Now they're actually pretty stable. But what it's doing is, what's actually happening here, it's just splitting up this malignant class into more and more classes. So it's saying, well, wait a second, those with the target tumor or a tumor that is actually malignant, there's more going on to that story versus the benign ones are staying together, right? So it's not actually splitting up the benign class at all until you go all the way up to 10. Now that's one thing that's going on. To the point of choice of parameters, that app alone will probably not give you an ideal parameter. It's more for exploratory analysis. There's statistical tests or other type of iterative tests you can use to find your optimal number of clusters. One of them, for example, is elbow method, where you just basically you plot the variance, the added variance of your clusters with respect to the total variance in your data set, and once it kind of plateaus, you know what you can approximate that way what number of clusters you should use, right? There's other statistical significance tests also you can use for your number of clusters. So this is more, actually what I found interesting about this app is a couple of things. If you go back down to your sample size here a little bit, you go to like say 45, your clustering actually is worse. You can see it struggles a little bit. Even you add one patient, and out of a sudden, the clustering is completely different. So you see, it's not really robust, and it's easy something to see. So my recommendation, seeing this, would actually go back and say, okay, a little bit more data would be good to have a more robust solution. But you can still learn things with that. For example, that 2 or 3 clusters are probably fine. Because if you add more here, you're really not gaining anything in terms of the question you're trying to solve, which is really just classifying your tumors into 2 different categories, right? Another observation that was made here apparently is that out of those 9 features that are driving your clustering, the clump thickness was found the least significant, and you can actually kind of visually derive that by it being fairly flat in color, whereas for those other 8 dimensions, they actually light up pretty brightly, and you can really see the difference of the 2 different groups. So that's another kind of visual inference you can make here, if that makes sense. Yes, please go ahead.
So I know there are lots of graphic libraries and packages and for all the visual stuff.
Mm-hmm.
So what is Shiny providing? Is providing or anything like the others?
Compared to what, for example?
I mean, there are lots of other graphic packages.
That's right.
That can do the same thing here.
Yes, that's right. That's right.
Shiny.
So for me, for my personal answer to this question will be, and I'm not really representing anyone's views on that one, but my own personal answer will be it's the interactivity that I like. I can use any type. If I'm a data scientist, again, I think most of us are data scientists. Most people at this conference are data scientists. If I'm a data scientist, I already work with R a lot, or let it be Python also, right? I can use a lot of my plotting routines and my analytical data monging skills, let it be dplyr, you know, for example, or like your analytical stack. You can already use that to create the app, so you don't have to go in a different environment. But on top of that, I would say interactivity. Interactivity is really good. And then also that it is open source from, it is open source all the way you go to your like final deployment in an enterprise setting, right? If I want to deploy this on my own website, I can also do it. Or if I'm going to deploy it and package it and send it to a friend, it's completely free, right? Like, or send it. It's really just if you deploy it at enterprise setting, of course you have a little bit of cost. You can outweigh that to your other options, right? But I think it's pretty good. It's coming from that open source background. There is other kind of emerging things in Python too, where I think Bokeh is very much built after that. It's built to match Chinese capabilities. I'm not an expert in Bokeh yet. I'm trying to become one. So once this happens, then we can also compare to Bokeh. But I think there's definitely other options. Not the only option, but I have started using Shiny, I want to say 3 or 4 years ago, and I've seen it come a long way from both functionality, but also adaptation, right? Adaptation in different environments, not just research, but also actually. It comes more from R, it's coming more from research setting originally, but it's pushing its way a little bit into enterprise setting as well, which I'm very keen to see. Another question? Sorry, can we?
You can use the Shiny library in the R Markdown. So what's the?
That's right.
Yeah, what's the advantage of develop some apps in R, use the app.R and finish at R, compared to I just use R Markdown and
Markdown.
use the Shiny library and then you get the same stuff.
So there were actually 2 sessions on R Markdown this week. There were 2 sessions on R Markdown this week. Did you see? I think on Thursday.
What I mean is,
yes.
I want to know why some people choose to write apps instead of just use that library in the Markdown. So what's the advantage of to write 2 files?
I think you could have standalone application, and you could also, you can share through a browser, right? Can you share R Markdown through a browser as well?
Yes.
You can, but it's more like notebook style, right? So this is like an app. I think the Shiny is more like a dashboard. That's like a fixed.
I wrote an entire website using R Markdown.
Okay. Do you want to talk to the specific difference to R Shiny? No. Speak to. So it's okay.
You have to install. Have to have a server, right? A Shiny server to
Yes.
to run this. In R Markdown, you can't do. You don't.
Yeah. But can you? But what's the limitation in data size? Is there any limitation? Are there limitations in data size? Oh, I think the data size might not be as big for R Markdown. Okay, we can talk after also about this one.
So when you run it and it opens up, it opens up in a browser.
Yeah. Because R Markdown can produce HTML, can produce PDF files, PowerPoint files.
When there's HTML, you can interact with it?
Yes.
There are lots of directive languages.
Yeah, you can embed in JavaScript.
Okay, I never saw that. It's good. We can wrap up.
So
It's
you
just
can interact
Q&A at
with
this point.
a generated graph.
I didn't think it would take 2 hours. People have left. That's good.
You couldn't do this.
Yeah.
You can inject data?
Yeah.
Here, because you're changing the number of patients, you're introducing new
This-
data,
yes.
and it's recalculating in the background.
Yeah.
Clustering.
You can do that. That's all.
I haven't. Yeah.
The server.
No, you can use JavaScript.
But you run in JavaScript. You run R code, or I don't.
Sorry?
You run the. But where does the R computations actually? Where do they run? He's saying the thing is the interactivity here. Moving this slider basically calls R again and calls H-class function again to redo the clustering on the fly every time. I don't.
You can put on a server.
Yes. So there is enhanced capability, right? So our Markdown is a little bit more reporting. I would say then, from like you have your result pre-computed. You can actually do a markdown probably if you just, for all your different iterations or for all your different instances of your clusters and for all your number of patients, you pre-run the clustering, you save it in some R data file, and then you can use R markdown. But it's maybe not the most dynamic solution and not most scalable, from what I understand. Depends on application, of course. Okay, so we have 5 more minutes. I'm going to stick around for questions. There's more other graph examples that I put in my GitHub. The second one was basically, we won't get to it now, but the second one was designed to learn how to plot charts in that beyond line charts and scatter plots. And I was encouraging you to basically use that on your own data set or use that on another data set you find online and see the possibilities there with those charts. But that was more explorative. I'm happy to follow up on that after the session also. But thanks for your time. Thanks for sticking around. So I'll get some lunch.
So thank you, Olaf, for such valuable insights on visualization and letting us know about this. Thank you so much. Have a big round of applause for Olaf.
Thank you.